Okay, so in section 5.4 here, we're going to be introduced to the constant E. And E is defined to be a fairly complicated expression. Limit, as n goes to infinity, of the quantity 1 plus 1 over n raised to the nth power. Now we can go ahead and put various numbers in here for n. For example, if n is 1, I would have 1 plus 1 is 2. 2 raised to the first is 1. But note, it said that we're looking at this expression as n approaches infinity, and we're wondering what happens as n gets really large, say 1,000,000, or 2,000,000, or 100,000,000, or 1,000,000,000,000, or 100,000,000,000,000, or 100,000,000,000,000 raised to the 100,000,000,000,000. And if that's the case, then this expression approaches a value, and it approaches a decimal about equal to 2.71. So as n gets larger and larger, we come up on a limiting value, which is about 2.71. And again, this is a definition. Now, why might this number, this constant, be useful for us? Well, let's look at the money world a little. So let's say we have something like the following situation. We have $100. We know that it's going to earn interest at 12% APR, and that's an annual percentage rate. And we want to invest our money here for, let's say, 3 years. And we're going to compound interest, means we're going to earn interest. We're going to see how much money our money is earned. And let's say we compound quarterly. Now, we could compound daily. We could compound yearly. We could compound monthly. Let's say we compound quarterly. Does that mean at the end of the first 3 months, which would be the first quarter, I get 12% interest on my $100? At the end of 3 months, I'm going to have $112? No. 12% APR means that however many compounding periods I have during a year, I'm going to have to divide that compounding rate up into those periods. So in this case, if I'm compounding quarterly, I'm going to have to take that 12% and I'm going to have to divide it by 4, which is fine. Now, if I were to multiply that 12% over 4 times $100, that would give me my amount of interest earned. However, I'm looking to know how much money I have at the end of those 3 months. So I actually want to multiply that by 1 plus 0.12 over 4, and I multiply my $100 by that. And at the end of the first 3 months, that's how much money I'll have. $100 times 1.03, which would be $103. So now I have $103 at the end of the first 3 months. What's going to happen next? Well, I'm going to go through another 3-month period, and I'm going to take the amount of money that I have now, and I'm going to multiply that by 1 plus 0.12 over 4. And that's how much money I'm going to have at the end of 6 months. And if we look at that, we can see that basically we're taking 1 plus 0.12 over 4 and squaring it. At the end of the second compounding period, I'd have $100 times 1 plus 0.12 over 4 raised to the second. So let's go ahead and generalize that. Then our amount of money then at the end of, let's say, n compounding periods is going to be $100 times 1 plus 0.12 over 4 raised to the n compounding periods. Well, we generally talk about investing for a year, and we talk about the annual percentage rate. So rather than writing it as n, let's say that we're going to look at our number of compounding periods here, which is, in this case, 4. And at the end of t years, then I'm going to have a total number of compoundings of 4t. And note, in this case, we have an n here and an n here, where n now stands for my number of compounding times per year. And my exponent, how many times do I compound? The number of times per year times the number of years. So you ask, how does E become involved in all this? Well, in general now we have the amount of money after a number of years invested at a certain percentage rate, compounding a number of times per year, is going to be given by this expression, principal times 1 plus rate over number of compoundings raised to the number of compoundings times years. You might say, well, we can compound quarterly, which means n would be 4. We could compound monthly, n would be 12. We could compound daily, which would mean n would be 365. We could compound 1,000,000 times during the year. And so what happens if we look at and let the number of compoundings approach infinity? And then, again, you should see that this is looking somewhat similar to our definition for E. Difference is we don't have a 1 up here, and we don't have this denominator matching this exponent. So let's see if we can do that. Let's see if we can manipulate this expression and get the definition of E here to pop out for us. Well, we definitely can get a 1 in the numerator up here if we simply reciprocate that r over n and write it in the denominator. We then want to match, thinking about our definition for E, which was the limit as n approaches infinity of quantity 1 plus 1 over n raised to the n. I want to match up denominator with exponent. So to do that, I want up here, I want an n over r, but ultimately I started with an nt. So how can I make sure that I keep this exponent up here equivalent to nt? Well, if I multiply n over r by rt, that's the equivalent of nt, and I won't have changed anything. This expression right here is equivalent to nt, the same as 4 over 2 equals 2. They're just different ways to write the same thing. But now I can go ahead and group this expression here, limit as n goes to infinity, p times 1 plus 1 over n over r raised to the n over r, and that whole thing is to the rt. Now go ahead and look what we have in here. We have this expression is n goes to infinity, that denominator and that exponent are both heading to infinity at the same rate. So what I have appearing in here, where the limit as n goes to infinity, is I've got my definition of E. And that means then that I can rewrite this then as P times 1 plus 1 over n over r raised to the n over r is E to the rate times time. This formula is known as the PERT formula. Principal equals, the amount of money you have after a number of years compounding continuously is principal times e to the rate written as a decimal. So if it's 12%, it would be 0.12. Time is always in years. So rate, make sure you write it as a decimal. And t is always years in this formula. P is your principal. That's the amount you initially invest. And it's, again, called continuous compounding because you've let your number of compoundings head toward infinity. So that means basically your money is earning interest, some interest, albeit a tiny amount, every instant that it's invested. And again, we can simply use our calculator option. We have an e to the x button on our calculator, so it's very easy to find a decimal approximation for this formula. Okay, so let's look at one example here. Suppose I've got $10,000, 5.62% APR. I'm going to do continuous compounding for 30 years. So I know I have then, my principal is 10,000. E raised to the rate I need to write as a decimal, so that's 0.0562, and the number of years is 30. So I then can go ahead and take my calculator, And what I would do in the calculator is I'd find that e to the 0.0562 times 30. So I'm going to use my second natural log function, which gives me an e to the x. And that is 0.0562 times 30, close parentheses. And then I'm going to multiply that by 10,000. And I get about $53,978.46. And actually, I would round down, so it's 46.4608. So it is 46 cents. Banks are not going to round up and give you more than what you've earned. So basically, if I look at this continuous interest in a 30-year period, I can more than quintuple my money with a 5.62% APR investment. Okay, so last concept here I want to talk about from Section 5.4, actually I think relates to Section 5.3 as well, is this idea of an annual percentage rate versus an annual percentage yield. APR, annual percentage rate, annual percentage yield, APY. Let's say I take $1 at a certain APR with a specified number of compoundings. See how much money you actually get, what your investment yields after 1 year. So we'll take a look at that. So here's my question. What's the annual percentage yield for an investment that's advertised at 7.82% APR, assuming daily compounding? So then I'm going to take, again, just for illustrative purposes here, take $1, and you're going to have then 1 plus number of, or rate is point, and I'm going to write that as a decimal, 0.0782. Number of compoundings were daily, 365. Raised to the 1 year, we're going to have 365 compoundings. So $1 times 1 plus 0.0782 over 365, raised to 365 times 1 year, or 365. So taking a calculator, getting a decimal approximation, I get 1.0813. So my dollar at the end of 1 year with 7.82% APR, compounding daily, yields me $1.0813, and that's an annual percentage yield of 8.1329%. So the annual percentage yield is a little higher than the annual percentage rate, and that has to do with the fact that you're compounding over a number of times during the year. What would you guess would happen if you again went up and rather than compounding daily, you went up and compounded continuously? Let's take a look. And indeed, if you guessed, that would be slightly higher, because as you're compounding more often, continuous compounding clearly is more compounding than daily, your actual annual percentage yield will go up slightly. We had 8.132% for compounding daily. When we compounded continuously, we added another tiny little bit, and that certainly is going to be our limiting factor for continuous compounding. That 7.82% yields about 8.13% annual percentage yield.